Okay, hey, what's up, guys? Module 4, we're going to talk about the last missing piece in everything that we need for the trifecta for parallel circuits. We ran through series circuits, we got everything down pat. We went through parallel circuits, but there was one portion that I left out intentionally because I felt it was a little premature to introduce it as soon as the book did. But now that we have a better understanding of Ohm's law and the relationship between voltage, current, and resistance, I think now is as good a time as any to bring in total resistance in a parallel circuit. But before we do that, let's go over a little bit of refresher. Okay, so in this really short video, at least I'm going to try and keep it short, we're going to go through a quick refresher about current and power in parallel circuits. We're going to talk about total resistance and two ways we can get total resistance with an example circuit, and we should be done. Let's kick it off. Okay, first, really quickly, we need to know some rules, or remember some rules about parallel circuits, and they're pretty simple. One, parallel circuit constitutes that there's multiple paths for a current to roll through when going from the voltage source to a ground. The second rule is a different amount of current through the branches of parallel circuits, and also the final one is that the same voltage runs across the junctions of parallel circuits. So we're going to visualize that in just a moment, so stay with me on this. Okay, cool. Let's talk about current in a parallel circuit. So I have a diagram up here. I gave the answer away, but I'm going to work through it with you so that you understand how we got there. Okay, so we've got a fairly simple parallel circuit. We've got a power source with 12 volts coming out of it. We've got two resistors in parallel, resistor 1 being 4 ohms and resistor 2 being 6 ohms. And we need to figure out some details before we even get to the point where we can start talking about total resistance. So let's whip out Ohm's law. It's our favorite tried and true friend. And first thing we need to do is we need to figure out the current running through each one of these resistors. So we know that the voltage is going to be the same across each of the resistors. Inherently, that's the nature of parallel circuits. So let's start with that. We are going to be bringing Ohm's law into the mix. V is equal to IR. And what we're trying to do is find out how much current is running through this guy right here, R1. Pretty simple it should be, right? Since the voltage is going to be consistent, let's replace what we can. We know volts, 12 volts is going to be here. We're trying to find the current, so we're going to call this I1 times the resistance we do know it's given to us. That's 4 ohms. Simple, simple. We'll call I1 is equal to 3 amps. And let's write that down so we don't forget this guy. So we've got 3 amps of current running down this resistor. Let's do the same thing to the other side, and we can use the exact same formula. We know the voltage is going to be consistent, and this time we're looking for I2 because we're talking about resistor 2. And this time 6 ohms is on this side. We've got 2 amps is equal to I2. Great. Let's mark this guy so that we recognize that. Now here's the thing. Without even collapsing this circuit down with total resistance to try to find out what the current or amperage coming out of the battery source, we can make some really good deductions. For one, we know that the amperage that's coming out of the battery must be equal to what's going into the battery, right? That's going to be a universal truth. We know that we shed 3 amps here at this first junction point. So 3 amps goes away. So whatever this amperage coming out of the battery is, we lost 3 off the bat. And then we have 2 amps that falls and goes past this junction over the resistor all the way back, where it's then joined with the 3 amps that it originally shed. So that means at this point we have 5 amps that are going back into the battery. Conservation of energy states that we also have to have 5 amps coming out of the battery. So before we even start to look at total resistance, we know exactly how much current is coming out of the battery just because we could do some simple deductions about what's going back in. Following so far? All right, excellent. It's also worth noting that each one of the junctions that we're passing through, 3 amps and 2 amps, equals the amount of amperage coming out. You're always going to have the total amount of amperage leaving a junction as went into a junction. All right, and that's what we see here. We've got our 5 amps coming out of the battery, shedding 3, 2 carry on, coming back around the bend, rejoined by our 3 amps, 5 amps going back in the battery. All right, so let's talk about power, because we didn't really get into detail in that last module, but it's worth mentioning that we have some tools at our disposal here. When we're talking about power, we essentially have two go-to formulas. There's three really, but let's focus on these two so that we can figure out how much power is going to be used up within components of our parallel circuits. The first one is power, which is measured in wattage, is equal to current squared times resistance. The second one that we can use is voltage squared divided by resistance is equal to power. Spoiler alert, I'm going to give you the answer to keep this video short. We have 36 watts used up in resistor 1, 24 watts used up in resistor 2. And we can walk through this if you want to. Let's get my head out of the way here. So if we were to use, let's say, the second formula on the first portion of the parallel circuit, voltage squared, so 12 volts, 12 times 12 is 144, divided by 4 is equal to 36. That's 36 watts used here, used up in this resistor. Conversely, we can use the other equation for this second portion of the parallel circuit, and that's pretty simple. We're taking the current squared, so that 2 times 2, 4, times the resistance, that's 6, 24 watts right here. Also worth noting, if you add up 36 and 24, you will get the total amount of power or wattage that's coming out of this battery, which we know is voltage times current. So now the final piece of the puzzle, and you'll have all the tools at your disposal that you need to solve any parallel or series circuit or combination parallel and series circuit, which is what the next video will be about. So we've got two formulas that we can break out if we need to. So let's take a look at the first one. RT, or the total resistance, is equal to voltage divided by total current. Total resistance is equal to voltage divided by total current. Let's take a look at this one. Alright, we cleared up some space to find out how we can utilize this formula. So let's take a look at it real quick. We've got our total resistance is equal to voltage over total current. So let's see how this would shake out for us. We know that our voltage is 12. Our total current is actually the current coming out of the battery, coming out of the source, right? So our total resistance is equal to 12 over 5. And I'll save you the math struggle. That actually is 2.4 ohms. Something worth noting here. When we're talking about total resistance in series, the total resistance is always going to be greater than any of the individual resistances, right? We're looking at the sum of resistance in series. The exact opposite is true when we're talking about parallel. We're always going to have a number that is relatively low for the total resistance when looking at any one of the individual resistances in the circuit, because we're separating the resistance between the different paths that the current could take. So if you ever have something where your total resistance is greater than one of your resistances, you might want to check your work and see where you went wrong there. Now, where total resistance is equal to voltage over total current sounds like a simple, straightforward way to go. It's not always the best way to go because typically we're not going to have the total current at our disposal. A more surefire way to do that is to use the traditional total resistance. And let me draw that to demonstrate what that is. First, I'll give you the formula. It's going to be, let's make this a little bigger. RT is equal to 1 over the first resistance value that we have plus any successive resistances that we may have for as many as exist in the parallel circuit. And all of this over 1. And it's the same as saying R1 over that, but that's a little confusing. So we'll take away any reference to harmonic mathematics out of the equation. The total resistance is taking the number of resistance values as denominators, summing them up as a denominator over 1. And that's pretty much it. Let me go through and I'll do the same thing just so that you can see how this is the same as the first equation that we checked out. Okay, so for our first attempt with our first formula, we got 2.4 ohms. That's using voltage over the current total, the total current, which is 5 amps. Just a refresher real quick, 12 over 5. 2.4 ohms, respecting that we're talking about resistance here. So let's look at the next phase, or the other side of that, which would be RT is equal to, we've got our resistance value, 1. Let's punch this in the calculator real quick. The easy way to throw this into Google, if we have harmonic or series resistances that we're trying to calculate. I'm going to share my screen and you can see that. So, pretty simple. We all know that the resistors are going to be the denominator here, but we got to set ourselves up using order of operations and grouping so that this is going to work out well for us. So let's start with going 1 over, and we know everything is going to be summed. All the groups, the resistors are going to be their own individual groups, but we need them summed. So we'll make one large group. And then for each resistor, within this group of the denominator, we're going to do an additional group. So we know we have 2 resistors. Let's throw those in there right there. So I'm just using parentheses to make these pseudo groups. We're going to sum those up. So we'll put a plus sign between any groups that we have. And we know the first resistor was 4 ohms. So that's the denominator, 1/4. And then the second resistor was 6 ohms, 1/6. Let's take a look real quick. Bam, that's exactly what we wanted. 2.4 ohms is the total resistance using only the number of resistors that we had and their known values. Pretty simple, right?